Hi students, now let's discuss about the SN1 mechanism. As we learned in the SN2 that a nucleophile first attacks on the carbon and then a transition state is formed. After that the halogen is lost and you get the product. However, SN1 mechanism is a bit different one. In the SN1 mechanism, the halogen is first lost, right? So what happens here in the SN1 mechanism? Halogen is first lost, and what you get? You get a carbocation, and then in the step number second, the nucleophile attacks. Okay, nucleophile attacks. So that means the intermediate which is formed in the SN1 mechanism is a carbocation. So this is a two-step process actually. In the SN2 mechanism, the nucleophile first attacks on the alkyl halide from the back side, and then a transition state is formed, and then you get the product. However, in the SN1, halogen is first lost. Suppose the chlorine, if it is chlorine, the chlorine will be removed as Cl negative. So there is a loss of minus, I can say X negative here. Okay. Halogen loss followed by the attack of nucleophile. So this is actually a two-step process. Let us see the mechanism in detail. You know the step number 1, in the first step what happens here? Halogen is lost, so this bromine comes out, and what do you get? You get the carbocation, carbon with the positive charge and the Br negative. In the step number 2, in the second step, this particular carbocation now is under the attack of nucleophile. But when you look at the carbocation has a hybridization of sp2, right? This carbocation, the intermediate here, it has the hybridization of sp2. So that means one of the p orbital remains unhybridized, and that is like this. Okay. These 3 alkyl groups and the carbon, these are in plane because the hybridization is sp2 for this carbon. In the alkyl halide, the hybridization is sp3, but over here the hybridization is sp2. And now the nucleophile attacks. See, the possibility is that the nucleophile can attack either from this side or from this side. There are two possibilities now, correct? If it attacks from here, from this side, these 2 groups will shift in this direction, and what do you expect? What type of a molecule you expect? It will be like this. Okay, these 2 groups will shift in this direction. If you have a hydroxide as a nucleophile, the hydroxide, once it attacks there, okay, from this side it will be this product. So if this is the A attack, this is the product A formed here. You can have the attack from this side also, correct? Then these 2 groups, they will shift to the other side. If it comes from here, if the nucleophile attacks from here, these 3 groups, they will shift in this direction. So you get a different configuration, right? So the product B is formed now if the hydroxide attacks from this side. Okay, so overall what we see, we find that the SN1 mechanism occurs in 2 steps. First, the formation of a carbocation, and the second step, the attack of nucleophile, and you get the product. And nucleophile can attack from the back side or from the front side. That means if you have a bromine here, either the hydroxide group will be exactly at the same position where the bromine is, or it can attack from the back side. Then these 3 groups, they will shift to the other side. That means 50% molecules will have a front side attack, 50% molecules will have the back side attack. So you know there is 50% possibility from there and 50% possibility from here. Now in the 2 steps here, the formation of a carbocation is actually a slow step. The first step here is the slow step, the second step is a fast. Formation of a carbocation is slow, but once the carbocation is formed, the nucleophile quickly attacks on it and forms the product. So the first step is the slow step, right? This is the slow step, which means that this is the rate determining step. So rate of a reaction now depends on the first step here, because the first step is the slow step, right? This is the rate determining step. And how many concentration terms you find? Only one, that is alkyl halide. The nucleophile takes part in the second step, right? The nucleophile gets involved in the second step. In the first step, in the formation of a carbocation, there is only one concentration term, that is alkyl halide. Hence we can say the rate of a reaction here depends on the concentration of alkyl halide only. It does not depend on the concentration of nucleophile, right? It does not depend on the concentration of nucleophile. It only depends on the concentration of alkyl halide. So only one concentration term. That's why this is called as a unimolecular nucleophilic substitution reaction, or SN1, right? 1. Why? Because we have only one concentration term on which the rate of a reaction actually depends. Okay, so now let's discuss about the SN1 again. Let's have a close look what actually happens here in the SN1. First step, which is a slow step. Okay, the bromine is lost here, Br negative is lost. You get a carbocation. Initially you had the sp3 hybridization here, but right now the hybridization is sp2. This is the planar molecule. Okay, so hybridization is sp2. The nucleophile can attack exactly from this side where the bromine was, or it can attack from the back side, because we have a planar molecule. This is planar, and nucleophile can attack from this side. If I call it as a front side attack, because we had the bromine exactly from the same position. So if the attack is from the front side, you get this molecule. The only difference is here, you can see here the S and S configuration is same, the bromine, and you have a hydroxide group here. Okay, with almost the same configuration. So there is retention of configuration, right? So this is the retention of configuration. Okay, here in this molecule there is retention of configuration. The configuration does not change, but the nucleophile can also attack from the back side. So over here the S configuration changes into the R, which means that there is inversion of configuration. Inversion of configuration. So there is a 50% possibility from here and 50% possibility from here. That's why you get a racemic mixture. So the mixture is a racemic mixture. Okay, fine. Now looking at the reactivity of the alkyl halides, reactivity order of the alkyl halides. If you have alkyl halide, as we discussed that the first step is the rate determining step, halogen is lost, so intermediate is carbocation, right? Now the stability of the different carbocations is that tertiary carbocation is more stable than secondary than primary, right? This is the order of the stability of the carbocations. Tertiary is more stable than secondary than primary. That means if you have a tertiary alkyl halide, it can easily undergo the SN1 mechanism, right? Because the carbocation formed is tertiary 1, which is the most stable. From a primary alkyl halide, it's very difficult to get a carbocation, right? Because that is quite unstable. So therefore the order of reactivity is tertiary is more reactive than secondary than primary. This is for the SN1 mechanism, right? This is completely for the SN1 mechanism. For the SN2 mechanism, as we have discussed already, that the alkyl halides, the methyl alkyl halide and the 1 degree alkyl halide, they normally follow the SN2 mechanism, right? And now the tertiary, it follows the SN1 mechanism normally. Okay, correct? So the order is opposite, right? SN2, you can see methyl alkyl halide, 1 degree secondary tertiary. SN1, tertiary secondary primary. Correct? So these two actually they follow what? They prefer the SN2 mechanism, while in the secondary one here, it can follow any one. SN1 or SN2, depends on the reaction conditions. Just we will discuss about it later on. And here the tertiary one, it follows the SN1 mechanism. Okay, so the net result is that tertiary follows SN1, the primary alkyl halide and the methyl alkyl halide, they follow the SN2 mechanism. A secondary can go either with the SN1 or SN2. Correct? Okay, fine. Now solvent is a very important factor here, right? Very, very important. If you have a polar solvent in the SN1 mechanism, we know that the first step is formation of a carbocation. That means you have to basically break the bond. Okay, the bond between the carbon and the halogen breaks first, and what do you get? You get the carbocation. The polar solvent helps in the formation of this carbocation, helps in breaking this bond. So if you have a more polar solvent, it will accelerate the SN1 reaction. That's why if you have this tertiary alkyl halide, okay, in a 100% polar solvent, right, with the water, okay, 100% polar solvent, reaction is quite faster than with the 90% acetone and only 10% water. In this reaction mixture, this is a little bit less polar solvent. Correct? Okay. So in the polar solvent, the SN1 reaction is accelerated. It becomes faster, quite faster. Okay. And that's why actually when we discuss about the different types of alkyl halides, right, their order of reactivity, whether they follow SN1 or the SN2, we know the tertiary alkyl halide follows what? SN1. Okay. And then the other side of it is the primary one. Let's suppose one alkyl halide. Okay, one alkyl halide, it follows what? It follows the SN2 mechanism, right? So if you have a tertiary alkyl halide, it follows SN1, primary alkyl halide, it follows SN2. What about the secondary? Secondary, they can follow SN1 or SN2 depending on the solvent. Here the deciding factor is, it can either go SN1, or SN2. It depends what type of solvent it is. If you have a polar solvent, right, it follows the SN1. Polar but protic, right? Polar protic actually. In the polar protic, to be more accurate, polar protic solvent, right, it follows the SN1 mechanism. While as in the polar aprotic solvent, right, polar aprotic solvent, it follows the SN2. So tertiary alkyl halide follows SN1, 1 degree alkyl halide, it follows SN2, 2 degree alkyl halides, it can follow SN1 or SN2 depending on the type of a solvent. If you have a polar protic solvent, it will be SN1. If it is polar aprotic solvent, then it is SN2. Right? Next point is about the nature of a leaving group. If the leaving group is a better leaving group, okay, a better leaving group speeds up a SN1 mechanism because you can get the carbocation quite easily, right? A better leaving group, the SN1 reaction is faster. So among the better leaving groups, among the alkyl halides, the I negative is a better leaving group, then the bromide, then chloride, and then the fluorides. Okay, so therefore for a particular alkyl halide, you can see the order of the reactivity will be iodoalkane, that will react faster than bromoalkanes. So this is the fast and this is the slowest. Hope you got the concept. Thanks for watching the video. Bye for now.